section 2.2, and we started talking about sets. And we talked about sets being a collection of objects. We talked about some ways of distinguishing between sets or describing them as being finite or infinite. We talked about the null set, that means a set with nothing in it, these kinds of things. Another thing that you might remember from doing contemporary math, if you took it, or from other classes, because they're commonly used across different classes as well, Venn diagrams. Who remembers Venn diagrams? Or you know kind of what I mean by it? A Venn diagram is just a diagram that's used to illustrate ideas in logic. So generally speaking, a Venn diagram has a rectangle and circles inside them. Okay? The circles overlap or they don't, they're one inside of another, all kinds of different descriptions. Basically, we've got a big rectangle with circles inside it, a Venn diagram. Okay? And we're able to use those to represent ideas in logic. Included in that description is a universal set. So a universal set means all of the items under consideration. For instance, if we're talking about all of the natural numbers, and we were describing some smaller portion of them, the universal set would be the set of natural numbers. Or if we wanted to talk about the universal set being everyone enrolled in Math 1 this semester, you guys would be the universal set, and then we could take a collection if you would describe it in some other way. Maybe you're also in earth science. Maybe if you're in science. Right. All right, so this is the idea though, okay? So the universal set is defined to be whatever the group is that you're talking about initially, okay? And complement is denoted as, so if we have a set F, then F with a bar on top of it, which is a different notation maybe than what you've seen in other courses. Your book uses this notation. F with a bar on top is defined to be all of the elements that are in the universal set that are not in the set F. Okay, all the items not in F. I don't know why that cursor won't go away. There it went away. Okay. All right, so let me draw a picture of this. So I told you that it was a rectangle, and so let's draw a rectangle. So here's our rectangle. There, I got a big rectangle. And if I have a set inside, we draw it as a circle or an oval or whatever. It's just a little, it better be inside. I'll let's see if I can do this features. So I've got a circle inside. This box, the rectangle, is the universal set. So everything inside the universe, right, of whatever description we're talking about lies inside the rectangle. The circle, let's call this set F. Okay? And so with set F, that would be set F. Okay? Just the part in the middle. F with the bar on top, the complement, would be everything outside of it. It's all the dead space and the white space outside. I'm not sure if this will work, but we're going to try. I didn't want that. How about that? That'll work. So F complement is out here, visually. So we can talk about shading in this sort of a way. We can talk about describing items in sort of a way, and I think that's where we're headed next, is the describing idea. Okay, so if U is the universal set, right, the set of all the students at OBU, A is the set of graduating seniors. We're going to, is that any of you? Is anybody graduating soon? No? So we're going to describe what A complement is. So first of all, the notation looks like this. Do you guys remember what the notation looked like in the different math book we had? It had an A and then it would have had a prime on the outside. And there's some books too that will use A and they'll put a little C on the outside.
What's the prime?
It means the same thing.
I remember that name.
All of these are the same notation. I mean, they're not the same. They mean the same thing. Yeah. So your book is using the bar on top. That's all you're going to see in this class. But if you've seen these notations, they're interchangeable and they're just confusing. All right, so we're supposed to describe that set. All right, so what is this complement in words? careful. And seniors aren't graduating. So can we say it a little bit more concisely? Yeah, we need to say something else. OBU students, yeah. Okay, so these are all OBU students who are not graduating seniors. Okay. So it probably would include most freshmen, sophomores, and juniors, right? Probably would include some seniors who still aren't graduating. Okay, but we want to be all inclusive in the most concise way possible. So we're going to go with that. All right, so I keep alluding to this idea of something contained inside of something else, and specifically that's called a subset. So for all sets A and B, are we okay?
Yeah. I usually sneeze like 6 times.
All right. My father-in-law has sneezed 10 times, I'm not kidding.
Yeah.
Who? My father-in-law, 10 times.
I've never been able to sneeze this time.
All right, for all sets A and B, B is a subset of A. This is how you write it. If and only if every element of B is an element of A. Okay. So if I were to describe the universal set as my family, 4 of us, my husband, myself, my son, and my daughter, a subset of my family would be boys, right? Because if I describe either of the 2 boys, then they're also contained inside of the larger group that I call my family. So a subset is simply a smaller grouping, or at least potentially a smaller grouping of the original group we're talking about. Now, a proper subset really is smaller. So it says for all sets A and B, B is a proper subset written. So let me show you how you write it. It's the same notation as the subset notation at the top, but it doesn't have the line underneath. And this is true if it's a subset already, and it's not equal to the set itself. So the example that I just gave you would have been a proper subset, right? Boys in my family. It would really be a set smaller than the set itself. But if I described to you a proper, or described to you a subset as the people in my family, that's my universal set. And then my subset is the people in my family who are over 4 years of age. That's actually all of us. It would be a subset, though not a very exciting one, because it's equal to the set itself. But it would not be a proper subset because it contains everybody. Okay? So you kind of leave out the idea of a set being equal to itself when you're talking about proper subsets. Now, there's a way of counting the number of subsets, and I don't think we've seen this in this course yet. So if a set has n elements, then there are 2 to the n subsets, and 2 to the n, and then minus the number 1. That's not minus 1 on the n, it's minus 1 on the whole thing. Minus 1 is the number of proper subsets. These proper subsets include all the subsets except for the set itself. So we remove that one possibility. Okay? So a set is a subset of itself. It's not a very interesting one, but it is one. It's no more interesting perhaps though than, no less interesting perhaps than the empty set. The empty set is also a subset of the diverse set, which is a little strange. So let's take a look at some examples. Consider a set of all the math faculty at OBU, and there are 4 of us. If you didn't know, just in case. There's myself, there's Dr. Marsh, you may have seen her before, and if you haven't yet, you will likely have her for either a Math 2 or a Math 3 course at some point, because she also teaches some of these. There's Dr. Hargrove. If you haven't had her yet, you probably won't. She's retiring this year. And then there's Dr. Nichols. And Dr. Nichols, if you haven't had him for one, you've still got lots of opportunity because he hasn't said he's retiring yet. So you can take him for a class if you would like to. So there's 4 of us. And we want to know how many different subsets are there of the math faculty. Well, the previous slide told you how to find that. What would you do?
2
2 to the 4th, which is how many? What is 2 to the 4th?
Where did the 2 come from?
The 2 is a part of the formula. Come back over here and take a
Oh,
look.
sorry, I was
Remember this?
confused.
Okay. The 2 is not a part of the situation. It's a part of, well, every situation, I guess. So it's a part of the formula.
Okay.
Yeah. And then 2 to the 4th, somebody was saying what it was. 16. So there are 16 different subsets. So if I said to you a subset of the math faculty met in front of Wood Science Center to talk about the weather, there are 16 different collections of math faculty who could have done that. I could be out there talking to myself. That's one option. So my daughter's come home recently singing the song that 8th grade Me Crazy. You guys know the song? I don't know all the words, but I know that one of the lines says something like, I called myself on the telephone, I asked myself if I was home, 8th grade Me Crazy. It's a line from the song, and so she's really funny singing it. All right. So this is, there would be a subset of 1. Very exciting. We also could have a subset of nobody, so there's nobody out there talking to nobody. That would be okay too. All right, so how many different proper subsets are there? 15. You just take one off. Now, the next example actually asks the question in reverse. It tells you how many subsets there are of something, and it wants to know how many elements there are in the group. So the easiest way to decide how that is to set up sort of an equation. This is actually talking about proper subsets. So what formula was the proper subset formula? 2 to the n minus 1, and that's going to equal to 127, right? So think back to algebra equations. What would you do next? Add 1. Let's add 1 today. That's okay. 2 to the n. And then 127 plus 1 is 128. And then either you just happen to know what the n would be, or you grab your calculator and you try a few things. And no matter which way you do it, you're going to figure out what n is. So it has to be a whole number, right? It's a number of items of something. So I can't get fractions or decimals. None of that's going to happen. What is n? 7. So n is 7. There's no work to show. You're doing it by process of elimination. Right? Just calculate. Okay. 7 elements of the group. Okay, are we ready? You guys are really talkative today yourselves.
How do you get
Sure, it's nothing related to math.
It's right.
So, Megan, you're the one who completely convinced me it had to be 7. Can you tell Cherish how you got 7?
Because 2 to the 7th is 128.
Literally look at it. Literally what she did, Cherish, she took her calculator and she tried 2 to the 4th, 2 to the 5th, 2 to the 6th, 2 to the 7th, and once she got to 2 to the 7th,
That's the explanation.
I was like, does that make sense? Yeah. Yeah, so that's what she really did.
Great teacher.
You guys are not encouraging my face. Don't believe me.
She'll be a fun time though.
She is.
My students are going to be stupid.
All right, let's take a look at the next example. Moving on. Example 7. We're going to fill in the blank. Okay, so you're going to have some problems, and all the problems you have are not going to have 4 options like I said at the top. They're either going to give you the first 2 options, element or not an element, or they're going to give you the options subset, not a subset. Okay, those are the 2 different sets of directions. I decided we could put them all together and answer both questions at the same time. Okay, and that's what we're going to do. So each of the blanks is going to have 2 answers, right? It's either going to have the answer element or not an element, and it's going to have the answer subset or not a subset. Okay, there's 2 answers in every blank. All right. So, empty set. That's what that says, right?
Yeah.
And the other one is the set that has the number 0 in it. Okay. It is not an element. That is right, Caitlin. It is not an element. Because this is not inside of it. Right? This is not an element. So there's the first symbol that goes in the blank. Second question then is it a subset?
I don't know.
You know.
Well, that wasn't the homework, so I just do it.
That's good.
Well, if you say, that's not 0,
is going to start to describe to me what is the empty set. It's a set with
No.
nothing in it, right? That's what you're saying, right? You're about to tell me that. The empty set is a set with nothing in it. So think with me for a moment. Are all of the elements that are in the empty set in the set with 0 in it? Yes. Because there's nothing in it to begin with.
How is it a subset if there's nothing in it?
Because we said it was.
You're such a sad answer. Well,
I'll take you.
in reality, I'm pretty sure that if I rewind the recording, I already told you the answer anyway. Just a minute ago, I told you that the empty set is a subset of every set. And it is. The empty set is a subset of every set. It's a subset of every set by default because of the language. Think about what the language was that defined a subset. A subset is a set where every element that's in it, and in this case, there aren't any, is also in the other set. So the nothing in this set is also over here because there's nothing in here to be talking about. Okay? The default is the empty set is always a subset of every set. Okay, so over here in this blank, got this one. Okay, let's do something that's not empty. How about this one? 15. Element or not an element? Is 15 an element of the set on the right? Why not? There you go. I like what you said at the end there, Lauren. The set on the right is all the numbers that have been multiplied by 2. How else do you describe all those numbers on the right? Even. They're even. This right here is just a fancy description of the even numbers, right? And 15 is not even. God. Yeah. Now, in between there, subset or not a subset? Not a subset. It's not a set anyway, is it? 15 isn't even a set. So it can't be a subset. All right? If it were a set, like had the curly braces around it and has 15, then we'd have a discussion and we'd have to decide. But this isn't even a set, so it certainly can't be a subset. How about this one on the right, or on number C? Curly braces 4. Is that an element of the set on the right?
Yes. No. Because those don't equal 4. None of those equal 4.
One of them does.
3 does.
1 plus 3 does.
There you go.
So does it have to be the same number every time?
No. There's something else going on with this. Nope, the adding one's not the problem. In the very same way that on 15, the one before with the 15 in it, those curly braces weren't there. Curly braces are actually present on this one, right? This is a set with 4 in it. It's not just the number 4. This is a set. If the curly braces weren't there, it'd be an element. Okay? Or if we had curly braces around each one of the items inside of this, then it would be an element, and that would be fine. But that's not what we have here. Right? It's a notation issue. The left-hand side of this equation, or this expression, basically on the board right now, is that this is a set with 4 in it. It's not the element 4 by itself. However, is it a subset? Yes. It's a set, and every element in it, namely the number 4, is in the set that's on the right. Are you tracking with me? Get some notes. Okay, so this would be fine. Whatever. That would be fine. 4 is an element. But that's not what I have here. this is the set with the element, or let's say containing the element 4. That'd even be better. This is the set containing the element 4. But it's a set. It is not an element. It is a set. And you know it's a set. Why? Because it's have curly braces around it. It's the language that's being used. But it is a subset because it's a set, and everything inside of the set, namely the number 4, is in the set on the right-hand side. It is a set. It's just not an element.
So can an element have the curly braces?
No. Well, let me pause there. I'll give you an example where it would. How's that? If you had a collection
So
of
basically.
sets over here, it could be.
Sets inside the set.
Yeah. Yes, then the elements themselves would be sets. That would be okay. But I don't have that down here, right? The elements here are not sets themselves. They're just single elements. Okay, let's do D because it's easy after all ones and go hard. What do you think? It is an element, right?
But it's not.
But it is not a subset. Right? It's not a subset. Okay. Fundamental principle of counting. Anytime you see the word fundamental, it means important. Basically, right? Fundamental means it's important. Fundamental. If an event N can occur in little n ways, an event capital N can occur in little n ways, then event M followed by event N can occur in n times n ways. So you need an example because there's lots of letters in what I just said. All right, so we're not going to do the examples up here just yet. Here's a practical example for you, okay? You go to Pizza Hut. We'll use Pizza Hut. And you have a choice of what crust you get on your pizza. You have a choice of we're going to make one topping pizzas, okay? And you generally, when you go to pizza places, they give you like 3 choices of crust. So let's say there's 3 choices of crust, okay? You have the little thin ones and you have the regular and you have the deep dish, right? 3 choices of crust. There are 3 ways. That's the capital M is the crust, and then the little m is the 3 ways. There's 3 ways you can choose your crust. Okay? Capital N is the one topping you get to pick. And I don't know, but let's say that there's 15 toppings. Okay? Because there's usually a lot of toppings at pizza places. 15 toppings. So the capital N is the number of, or is the kind of topping you pick, and the 15 is the little n, is the number of options you have. And the question is, how many different one-topping pizzas could you create? And the answer is, 45. 3 times 15. Okay? So you're multiplying the number of ways different things can happen. And I always give this example when I teach this, and no matter what courses. Have you guys ever seen the deal at Sonic where they put up the, 1 million things or other ways you can create a drink option with Sonic? That's what they're doing. Theirs is a little more complicated because they can put 2 toppings in, or not toppings, so 2 flavors in or 3 flavors or whatever. I suppose they can probably mix them all together and that counts as one as well. It's a little bit more complicated process, but it's the same process, right? Just exponentially more complicated, I guess, but the same process. So we're going to take a look at some items here that have that same idea, all right? So here is example 8. How many 4-digit phone number extensions can be created if? So there's 4 items. So I don't just have M followed by N. I have M, N, Q, and R, or whatever. I've got 4 different things I've got to pick. All right? And I like to write out placeholders for those 4 different items, no matter what they are that I'm picking. And the first statement, part A, says all 4 digits can be any value. How many different values could go in the first placeholder? 10. Numbers 0 through 9, right, Kayla? Yeah. And if it can be any value, how many different choices do I have in the second digit of my phone number? 10. And the third? And the last one? And I multiply them because that's what the fundamental principle of counting says I'm supposed to do. And what happens when you multiply 10 by itself 4 times? I think you get 1,000. No, 10, that 1, 2, 3, 4, you get 4 zeros. The zeros there, 10,000. There are 10,000 different phone numbers that you get if you only vary the last 4 digits. Okay? Part B is different. Part B says you can't repeat. Now, that doesn't necessarily make sense in terms of phone numbers, but just work with me on what we do when things don't repeat, because that's what I'm trying to show you in the problem, okay? Not necessarily that it makes sense in terms of the context, but I can do the same thing. 4 digits. How many choices do I have when I punch in the first digit on the phone number? I have 10. Now, I can't use that number whenever it was again, so how many choices do I have for option number 2? 9. And then 3. And we multiply them because that's what the fundamental principle of counting says we're supposed to do. And what do you get when you multiply them? Half as many, almost, right? Just because you couldn't repeat the digits. Are we all good? You didn't like the set stuff, but right kind of counting stuff? Okay. All right, let's do one more. We're going to go to the wall. That's good, right? Yeah. I created a problem because you guys were all women, and I figured you might want to go to the mall. So we're going to go to the mall, and we have 5 favorite stores apparently in this problem. But we only have time on part A to go to 3 of the 5 stores. Okay? So we only have 3 blanks, because we're only going to go solving at 3 shops. And if we then spend too much time, we may not be able to go all 3. But that's this way. We're going to go to 3. Okay. How many choices do I have when I start? 5. Now, this particular problem did not say there's no repeats. But you know there's no repeats, right? The nature of the problem tells you that you're not going to, well, I will tell you, I did at Walmart yesterday. I went to the store and then I left and came right back in. But that's a different story. That's not what's going on here, right? That's not the normal thing people do. They don't normally walk out to their car and go right back inside. Okay, so after I've chosen my first favorite store to go to, how many choices do I have after that? 4. And then 3. And we multiply by the fundamental principle of counting. And we get 60. There are 60 ways in which I could choose those 3 stores and in what order. But what if we get to go to all 5? How does that change things? I need 5 lines. And what numbers go in them? And of course I multiply because this is fundamental principle of counting. What do I get? There are 120 ways to do that. And then I want you to create an example. We'll talk together and we're going to think about it. This is why I was spilled beans last time. Hold my example. Create an example together here of the null set used in real life. So, the idea is we need to create a set that's empty. Describe something like that. Okay, I'm going to give you an example, and then you have to describe something after my example in your life. My example of a null set is the set of teenagers living in my house. So Lauren and Megan know, and Caleb probably does too. How about how old are my kids? 4 and 7. 4 and 7. 4 and 7, neither of which are teenagers. And I know I look young, but I'm not a teenager either. So I don't count. My husband is older than I am, so he doesn't count. And unless you count the animals, we have no teenagers. That actually call that right. So that would be an empty set, right? I can tell you till the day is long how wonderful the teenagers are that live in my house. They're perfect angels. They clean up after themselves. They put their dishes in the dishwasher, do their own laundry. But they don't exist, right? That's an empty set. Somebody describe one for me.
My kids.
Wow. Kayla's kids. They're wonderful, aren't they, Kayla? They're angels. Kayla's kids are wonderful. What else? Oh, Kayla's boyfriends, they're so kind, and they show up at the door on time. And these boyfriends. Okay. What else? The number of pens? Pets. All right, so Rachel's pets. Rachel's pets, they all live in her dorm room, and they're creating all kinds of mess there right now. They don't exist, right? Did you get the idea? We can describe empty sets. All we have to do is describe a set with nothing in it, okay? We can talk about all of the negative natural numbers. They're great. Negative natural numbers are the best numbers you're going to ever encounter. They don't exist, because the natural numbers are the counting ones, the ones you count like when you're a little kid, 1, 2, 3, 4. If I said -5 to my son, he would have no clue what I'm talking about, right? It's not a there isn't a negative natural number. All right, so enough about empty sets. All right, we'll stop.